Okay, so this is a video on elementary matrices and um, matrix decomposition. The idea here is that we're going to make a relationship between invertible matrices and row operations. So if you remember, we had three row operations. You could exchange two rows. You can multiply a row by a non-zero constant. And last one, you can add a multiple of a row to another row. Okay, so this is going to bring us to this idea of an elementary matrix. Okay, so basically an elementary matrix is a matrix that you can take the identity matrix and perform a single row operation on it and get that matrix in return. So these have to be square matrices, right? So elementary matrices have to be n by n. So here's an example of an elementary matrix. If I have the matrix 1, 0, 0, 0, 3, 0, 0, 0, 1, this is an elementary matrix because I took the identity matrix, I took row 2, multiplied it by 3, and stored it in row 2. Another example could be something like 1, 0, 0, 0, 0, 1, 0, 1, 0, and this would be taking row 2 and row 3 and exchanging them. Or like I could have the matrix 1, 0, 2, 1. And this would be take 2 times row 1 and add it to row 2 and store that in row 2. Each of these is an example of taking an identity matrix, performing exactly one row operation on it, and getting an elementary matrix. Okay, so this gives me this idea of left hand multiplication. Okay, so if I take an elementary matrix times some matrix, it will perform the row operation that's kind of like within that elementary matrix. So, for example, this would be the elementary matrix where I would exchange the row 1 with row 2, right? So this is exchange row 1 with row 2 with the identity matrix and get this matrix. Now, what's spooky here is that if I multiply that by some other matrix of a decent dimension, right? That product, if I do that multiplication on the left-hand side, will actually perform the indicated row operation. So if you multiply these two together, and you could try this using MATLAB and see what comes up, you'll end up with 1, negative 3, 6, 0, 2, 1, 3, 2, negative 1. So it'll actually perform the row operation. Like another example of this would be like if I took 1, 0, 0 times 0, 1 half 0, 0, 0, 1. Okay, so this should be the row operation that says take 1 half of row 2 and insert that in row 2. And if I multiply that by 1, 0, negative 4, 1, 0, 2, 6, negative 4, 0, 1, 3, 1, what I should end up with is 1, 0, negative 4, 1, 0, 1, 3, negative 2, 0, 1, 3, 1. It will perform this row operation right there. Okay, so that's pretty wild. Okay, so a couple of things here. all elementary matrices are invertible. And in fact, the inverse of an elementary matrix is an elementary matrix. It basically undoes the row operation. Okay, so this is kind of an interesting reality. The next piece in this is that if you have an invertible matrix, it can be written as a product of elementary matrices. And in turn, any product of elementary matrices is an invertible matrix. So it's invertible if and only if you can decompose it into a product of elementary matrices. So we're actually going to walk through this with like a 2x2 case and show how this decomposition can be done. Okay, so let's start with the matrix. A being -1, -2, 3, 8. Now this is an invertible matrix, okay? So what we do is we kind of play the Gauss-Jordan game by hand. Alright, so the first move I'm going to do here is I'm going to take -1, and I'm going to multiply that by row 1 and stick that in row 1. Now, the matrix that says to do that would be -1, 0, 0, 1. That's the elementary matrix. I'm going to call this E1 inverse. Okay? Now, just bear with me on why that's going to be. So if I multiply E1 inverse by -1, -2, 3, 8, I'm going to get 1, 2, 3, 8. Okay, so now I've got to get rid of this 3. Right? So I'm leaving the first row alone, and then I'm going to multiply the top row by -3 and add that to the second row. So we're going to call this one E2 inverse. Alright, so let's see. We're going to multiply that by this guy, 1, 2, 3, 8. That's going to give me 1, 2, 0. 2 times -3 is -6 plus 8 is 2. Okay, so I need this 2 to be a 1. So we're going to take this and we're going to leave the top row alone, and we're going to multiply the bottom row by 1/2. Right? And if I do that, times 1, 2, 0, 2, I should come out with 1, 2, 0, 1. Okay, so this guy is now E3 inverse. Okay, so what do I need? I need this to become a 0, so I'm going to multiply bottom row by 2 and add it to the top row, so that's going to be 1, 2, 0, 1 times 1, 2, 0, 1. Oh, that's kind of wild, right? They happen to be this one's got to be -2, right, in order to make that work. So I have to multiply the bottom row by -2 and add it to the top row. Aha. So it's really close. And if I do that, I'm going to end up with the identity. So we're going to call this guy E4 inverse. So if I follow this out, if I take, let's see, I took A, and I multiply that on the left by E1 inverse, then E2 inverse, then E3 inverse, and then E4 inverse, which gave me I. Okay, so what we do is we look at this and we say, well, multiply both sides by E4. Because if this thing is invertible, it has to have an inverse, right? So if I multiply both sides on the left by E4, I get E3 inverse, E2 inverse, E1 inverse A is equal to E4. Now I multiply both sides by E3. Well, that's going to give me E2 inverse, E1 inverse A is E3, E4. E4 on the left. Now multiply the left side on both sides by E2. It's going to give me E1 inverse A is E2, E3, E4, and then multiply again by E1. I get A is E1, E2, E3, E4, and voila! A is the product of 4 invertible elementary matrices. So if you actually take those inverses, let's take a look at what you would. Okay, so if I took so I now have that A is E1, E2, E3, E4, right? And E1 is the inverse of E1 inverse. And if you actually took that inverse, you would get -1, 0, 0, 1. The inverse of E2 inverse, also known as E2, would be 1, 0, 3, 1. The inverse of E3 inverse would be 1, 0, 0, 2. And then the last one is 1, 2, 0, 1. So this is an elementary matrix decomposition of A. It's a product of elementary matrices that would get me A. This introduces an idea that we're going to call row equivalence. So if I have A and I can multiply A on the left by some product, I equals 1 to n of EI of elementary matrices, and get B, then I say that A is row equivalent to B. Okay, so why is this significant, right? If I can get from one to the other by using product of elementary matrices, they are what we call row equivalent. Okay, so this is going to get me to my first equivalent conditions theorem, which are kind of important in linear algebra. Okay, so we have a bunch of equivalent, there we go, conditions. What this means is that I'm not spelling real well tonight, conditions. What we've got going on here is that each of these statements are either all true or are all false. So if A is an n by n matrix, so it's going to be square, the following things are all equivalent. 1, A is invertible. So if A is invertible, then AX equals B has a unique solution. The homogeneous systems of equation, AX equals 0, has only the trivial solution. Number 4, A has to be row equivalent, okay, there it is, to the identity. So you have to be able to get A by multiplying a bunch of elementary matrices times the identity. And last, A can be decomposed into a product of elementary matrices. If any of these 5 things is true, they are all true, and if any of these 5 things are false, they are all false. So this is our first equivalent conditions theorem. It won't be our last. This list is just going to keep growing of things that are all logically equivalent to each other. All right, so there you go. That's elementary matrices and matrix decomposition.